So, infinite sequences series. This is chapter 10, section 1. A sequence is a type of infinite list of elements. We call those members of that list. A series is an infinite sum of values. The values are the elements in that list. So, for example, so a list of these this bracket tells us it's a list, the list of elements in that sequence. So in this one, our list would be square root of 1, square root of 2, square root of 3, all the way square root of n, and this all keep on going to infinity. A series would be a specific list of those numbers. Because here I can take those and add them all together. So here we have square root of 1 plus square root of 2 plus square root of 3 dot 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 square root of n plus dot dot dot, and keep on going forever. It's a sum of an infinite series. There are two ways we can represent these things. Well, what would that sequence look like? What would that sequence look like? So here we have the first one. When n equals 1, what do we get? Negative 1 to the power 2 is 1. 1 over 2. Or 1 over 1, which is 1. When n equals 2, the second number in that list, negative 1 to the power 3 is negative 1, so the answer is negative 1 over 2. When n is 3, so 3 plus 1 is 4, so it's going to be positive 1 over 3. So just take n, plug it in there, and work it out. When n is 4, 4 plus 1 is 5. Negative 1 to the 5th is negative 1 over 4. You notice they alternate values. What's that one going to look like? Now, when n is 1, we have 1 minus 1 is 0 over 1 is 0. When n is 2, 2 minus 1 is 1 over 2. When n is 3, so it's 2 over 3. And we see a pattern here. Because the top's always going to be 1 less than the bottom. Negative 1 n plus 1. So what's the first one? 1, second, third. Right, it just alternates. 1 plus 1 is 2, negative 1 squared is positive 1. 2 plus 1 is 3, so it's odd. So we have that sequence. That's called an alternating sequence. Now, let's look at how we would graph these. I'm trying to find what's the easiest to graph. Let's look at the last one. To graph sequences, let's look at the last one we had, which was -1 n plus 1. There are two ways we can do it. So we have -1, 0, and 1. So what's the first point we have? -1. Oh, no, it's +1. So we put a dot there, call it D1. What's D2? The second point, -1. So put a dot there, call it D2. The third point is 1. So it's also D3 and D4. That's one way to do it. We could plot the points on a number line and label what they are. Or this, we do a XY type chart where this is our counter. In this case, it's D sub n, and this is our n. So when n is 1, what do we get? We get +1. When n is 2, what do we get? -1. When n is 3, we get +1, and so on and so forth. So we can represent them that way. Convergence and divergence. So here's the definition. The sequence A sub n converges to a number L if for every number epsilon there corresponds an integer n, capital N, such that the sequence minus the limit is less than epsilon when n is bigger than some number capital N. So this is what convergence means in sequences. The sequence a sub n converges to a number L if for every positive number epsilon, there corresponds an integer n such that the absolute value of a sub n minus L is less than epsilon whenever n is bigger than n. What does that mean in English? What if it doesn't? What if this isn't true? What happens? Else it diverges. It diverges if no L exists. That's what that means. So here's notation. If the sequence a sub n converges, we write a sub n goes to L. Because what does this mean? We did this in chapter 2. What that means is the limit as n goes to infinity, a sub n equals L. But now we're giving it a name, other than just as a limit exists. So if the limit of some sequence as n goes to infinity is a value L, then it converges to that value. Let's look at some examples. Let's put some meat on this table. Example 1. Show the limit as n goes to infinity of 1 over n equals 0. We have to use that absolute value thing we just talked about, where a sub n minus L is less than epsilon when n is bigger than n. We have to use that. So how do we set this up to look like this? The absolute value, what's a sub n? 1 over n. What's L? Zero. Is less than epsilon when n is bigger than some value n. So what this says is 1 over n, absolute value of 1 over n is less than epsilon, is true when? Is true when 1 over n is less than epsilon, or if we flip both of these, n is greater than 1 over epsilon. Remember, this doesn't help us much if it's in this form, 1 over n, because we have to compare n's. So 1 over epsilon has to be bigger than some value n. And n can be what? Capital N is any integer greater than 1 over epsilon. So what does all this stuff mean? Does it satisfy our conditions? So is 1 over n less than epsilon? Yeah, the bigger n gets, the smaller it becomes. So it's going to be less than epsilon. That's true. So with that, we drop the absolute value sign and we get n is greater than 1 over epsilon. So n is greater than n. So 1 over epsilon is greater than n. So what does that tell us? 1 over epsilon is pretty small. That means the value we pick for n is also pretty small. So the bigger epsilon becomes, the smaller n becomes, which means what? Which means we approach our value, our a sub n equals L. B, the limit as n approaches infinity of k equals k. Remember, we have to use the a sub n minus L is less than epsilon when n is bigger than capital N. So what's a sub n? What's L? K as well. We know that epsilon has to be a positive integer, a value, not an integer. It just has to be positive. So what this gives us is 0 is less than epsilon. According to this, whenever n is bigger than capital N. So is 0, remember, epsilon has to be a positive number. Is 0 always less than n, less than epsilon? If epsilon is a number greater than 0, can it equal 0? No. So 0 is always strictly less than epsilon. So this is true for any n. So it's always true. We have a lot of terms, elements that we have to compare to. But that's why it's very important. If you have any questions, refer back to the theorems. It has to match each of the conditions that are stated in the theorem, and then we have to use the right formula. Example 2. Show that 1, -1, 1, -1, 1, -1, ... -1 to the power n plus 1, ... Diverges. Actually, I should have said, show that the sequence a sub n, which equals to -1, show that this function diverges. How do we do that? Because remember, we have to have a sub n minus L is less than epsilon when n is bigger than some value of n. We also notice that our numbers are always oscillating between 1 and -1. So let's pick a number that's between there. Not 0, yeah, let's look 1/2. 0 is going to be too easy. Because if this is 0, can this number be less than 0? No. So it can't be 0. So let's pick epsilon equals some number like 1/2. Because that's between 0 and 1. So what do we know? We know that the well, we have 2 bounds. We have upper bound and lower bounds, but the absolute value of 1 minus L is less than 1/2. We're doing the top bound. So if we drop the absolute values, what happens? If we drop the absolute values, then it has to be between those 2 values, the positive and negative 1/2. Subtract 1 from everybody. So that's negative 1/2 minus 2/2 makes it negative 3/2. One half minus 1 is negative 1/2. So far, so good. We have to change the sign. So we have to change everything, the signs, the inequalities, everything across the board. So it says 3/2 is greater than L, which is greater than 1/2, which can be rewritten as 1/2 is less than L is less than 3/2. So that's the range of our L. When it's positive 1. What happens when a sub n is -1? The other number in our list, the other bound. So we have here is -1 minus L is less than 1/2. If I drop the absolute values, I got negative 1/2 is less than -1 minus L, which is less than 1/2. Now I got to add 1 across the board. So 1 minus 1/2 is 1/2. 1/2 plus 1 is 3/2. I gotta change everything across the board, all the signs and all the inequalities. So I got negative 1/2 is greater than L is greater than negative 3/2, which this tells us negative 3/2 is less than L, which is less than negative 1/2. What does this tell us? Can L be between this domain and this domain and this domain? Are they the same domain? No, they're not. Those are negatives. These are positives. Since L cannot be in two places at once, it diverges. Oscillating functions diverge. Always. Again, when I ask a question, I want you to think through it before answering. Because I mean, you answer questions faster than I could ever answer questions. Because I take time and read it and think about it, work it through. Don't just spit out the answer. An answer, not the answer. So because we had our oscillating function, it could be positive one or negative one, we have to look at both of those when A is positive and A is negative, and then solve them from there. Right. Diverges to infinity. The sequence A sub n diverges to infinity if for every number m there exists an integer n such that for all little n's, which are greater than n, the sequence of A sub n diverges to infinity if for every number m there exists an integer n, such that for all n's, which is larger than n, we get am is greater than m. That makes more sense. If the sequence A sub n diverges to infinity, if for every number m, capital M, there exists an integer n such that for all of the n's, which are larger than n, an is greater than m. Now, here's this condition of it. If this condition, oh no, is true, then we say that the limit as n goes to infinity of A sub n goes to infinity, or A sub n goes to infinity. It's similar for negative infinity, except the values, instead of for some integer n such that n is larger than n, it's the opposite numbers. So A sub n goes to negative infinity as a negative. It could go to positive and negative infinities. All right. Calculating the limits of sequences. Remember, sequences is just a list of numbers. We want to know how we calculate these things. Okay. Here's a theorem. let the sequence A sub n and B sub n be sequences of real numbers. And let A and B, capital A and B, be any real numbers. As we saw, it can be positive, it can be negative, or it can be zero. What are real numbers? Anything between negative infinity and positive, but it's a finite number. Let the sequence A sub n and sequence B sub n be sequences of real numbers. And let capital A and capital B be real numbers. Then the following rules hold if the limit as n goes to infinity of A sub n equals capital A, and the limit of as n goes to infinity of B sub n equals capital B. So again, before we move on, we have to understand what this says. We can read it, and we think we understand what it says. But what does this tell us? What do we have to make sure about our sequences before we move on any further? Has to be real numbers, first off, yes. Yeah, don't think it's obvious. No, it's important because can they be anything but? Can they be non-real? Yes, you can have imaginary numbers. Think of it this way. What if I had the sequence of 1 minus 2n, where n is 1 to infinity? No, those are all going to be imaginary. So I can't do this. You can't go any further with that. So it is possible to have imaginary numbers, non-real numbers. And let A and B be real numbers. Why? Because those are the limits. Those are the values that the limit of those sequences go to. Now, I know you've seen these before, but here we go again. The sum rule. The sum rule says the limit as n goes to infinity of the sequence A sub n plus B sub n is equal to A plus B. Why? Why is that true? We have to go back to the basics. Whenever you have a sum of limits, we can break those down. We can take the limit as n goes to infinity of A sub n plus the limit as n goes to infinity of B sub n. And remember, as it's stipulated, the following hold. If the limit of A sub n equals A, is equal to A, and the limit of B sub n equals B. So the limit of A sub n equals A plus the limit of B sub n equals B. Same thing works for the difference rule. The limit as n goes to infinity of A sub n minus B sub n. Same reasoning, which give us A minus B. Because we can split them up. The constant multiple rule. The limit as n goes to infinity of some constant times my sequence. Because it's a constant, I can take it out in front. So the constant times the limit, which is a. The product rule. Product means what? Multiplication. So the limit as n goes to infinity of a sub n times b sub n is equal to the limit as n goes to infinity of a sub n times the limit as n goes to infinity of b sub n. The limit of a sub n is a, the limit of b sub n is b. I'm apprehensive of the way they freely put that dot between there, because later on in Cal 3, we're gonna look at cross products and dot products. And it's different ways you approach and calculate these things. But in this case, they're saying is a times b instead of a dot b. So again, you'll learn a lot of, and that's where you understand why in my algebra courses, whenever I ask them how many, that's why I never use the PEMDAS rule. In my classes, if anybody says that, pretty much I kick them out of the class right there. Because it's so fake. What does PEMDAS stand for? Parentheses, exponents, and then what? Is that all the special operations? No, we in this class alone just talked about another 30 or 40. There are over 400 different ones that we haven't even talked about. So that's why PEMDAS is such a waste of time. If you're going to learn it as the order of operations, which is what it's called. And the last one is the quotient rule. It says the limit as n approaches infinity of a sub n divided by b sub n is equal to the limit of a sub n divided by the limit of b sub n, which is equal to a over b, as long as b does not equal 0. Let's take an example here. I know, have we seen these type of rules before? Yes. And we'll see them again a couple more times in these courses. Example 3. The limit as n approaches infinity of -1 over n, using the properties we just learned, what does that equal? Well, here's our constant, -1. So we take the negative, put that in front. So then we can use the quotient rule. The limit of 1 as n approaches infinity over the limit of n as n approaches infinity So 1 over as n goes to infinity, it becomes infinity. 1 over infinity equals what? As n goes to infinity, it gets smaller and smaller and smaller and smaller. Now, this was the long way. We knew that was going to happen here. As n gets bigger, this fraction gets smaller, so it goes to 0. The limit as n goes to infinity of n minus 1 over n. What the properties don't tell us is before we do anything, we can algebraically manipulate this. Because whenever you have a monomial on the bottom, and an equation up on top, we can separate these into individual terms. N over n is 1. Now, let's take it. When n goes to infinity, 1 stays where it is. What happens to 1 over n? It goes to 0. So it equals to 1. The limit as n goes to infinity of 5 over n squared. 5 is a constant. It goes out in front. So we have 1 over n squared. So what happens when n goes to infinity? It gets smaller, it goes to 0. Now this is C and this is D. I'll do it. We have the limit as n goes to infinity of 4 minus 7 n to the 6, n to the 6 plus 3. What do you think you do here? Hmm? If you did the quotient rule, what would that give us? Well, let's see it. Let's do it, and I'll show you a shortcut, which we talked about it already. But yes, use the rules as they gave us. So we have a limit as n goes to infinity of 4 minus 7 n to the 6 over the limit as n goes to infinity of n to the 6 plus 3. Because this is a difference rule, and this is the sum rule, we'll have the limit as n approaches infinity of 4 minus the limit of 7 n to the 6. Then we have the limit of n to the 6 plus the limit of 3. You see here what's going to happen is we have a problem. Because if we continue in this logic, the limit of 4 is 4. The limit of 7n to the 6, as n goes to infinity, it goes to infinity. This one, n to the 6, it goes to infinity, plus 3. Okay, since we have infinity over infinity, what do we do then? L'Hopital's rule. So we have the limit as n goes to infinity of 4 minus 7n6 over n6 plus 3. It was, yes. Take the derivative of this. We get the limit. 4 goes to 0. 7 times 6 is 42 n to the 5th. 6 over 6 n to the 5th. So what we're left here is the limit of negative 42 n to the 5th over 6 n to the 5th. Anything cancel? Yeah, the n to the 5ths can cancel. So we're left with negative 42 over 6, which is negative 7. Okay, that's using the rules. There's a shortcut. Whenever you have rational expressions, with different, same or different degrees, it doesn't matter. What we have to do, since we're going to infinity, we're trying to get things in terms of some number over n, because as n goes to infinity, this number goes to 0. So at this stage in algebra, we learned the asymptotes. Whenever you have a degree on top and bottom, this is the horizontal asymptote, by the way, divide everybody by the largest degree. The largest degree is n to the 6. So if we divide every term by n to the 6, so each of these terms are divided by n to the 6. So we have 4 over n to the 6. These cancel, so we have minus 7. These cancel, so we have 1. As n goes to infinity, that goes to 0, that goes to 0, so we're left with and there's even a shortcut. Because the largest exponent, the leading term, the term with the largest exponent is the most important part in the function. Anything less than the highest one, we just forget about. So we have negative 7 n to the 6 over n to the 6, which is negative 7. Yeah, it gets shorter and shorter and shorter. But again, all this stuff goes back to the rules of algebra. Holy smokes, I didn't realize there's so many sections in this part. We'll stop here. We're going to start off next time on something called the sandwich theorem. which we've used since chapter 2. That's why we said if the limit as x goes to infinity of sine x over x equals 1. Here's the proof of it. So we'll do that when we come back after a very beautiful, relaxing weekend. Yes.